Hello everyone, welcome back. We are going to start off with a probability question on basketball. So imagine you are shooting free throws and you make your first shot and miss your second one. After the second shot, every free throw you shoot has a probability of going in equal to the proportion of made free throws up to this point. So because you made your first one and missed your second one, you have an initial probability of scoring equal to 1/2. If you then make that third one, now you've made 2 shots out of your 3, so your probability of scoring is now 2/3. What is the probability that you score exactly 66 in 100 total shots? So let's think about this for a second. Your first instincts might be to go to some type of Markov chain where the result of what you do at a given step is purely dependent on your results at the step before. And that's very true. I think the calculations might get a little iffy with that one. So I am approaching this from a much more direct aspect and kind of manipulating some of the algebra and multiplication that we do. So let's just think about this in terms of the actual paths or the ways you can score 66 baskets. So you're going to first start, and I'm going to represent, so we're going to have our path, and I'm going to represent this as a binary string. So where a 1 is going to be equal to a make, and a 0 is going to be equal to a miss. So if I made the first one and missed the second one, every string I have will go 1, 0, ... And then whatever happens over here, I know if we're just looking at the paths that give us exactly 66 made shots, then we know there are 66 ones and 34 zeros. Now, let's think about how we could actually make a path like this. Well, this is just a simple counting problem. If we want to have 66 ones and 34 zeros, and one thing to note is that these are already fixed, then what we're actually doing is we're placing 65 ones in 98 spaces. And that's a very simple thing to do. We know how to do that. There are 98 choose 65 ways to do this. And then once you place the ones, the zeros predetermine themselves. So that's how many ways we can make a path like this. But the art of this problem is that those paths might not be equally likely, because the probability at each step is dependent on what you did the step before. So I could get to 66. Maybe this is my 66 made shots right here. I could come from having 65 made shots or 66 made shots and missing one. And the probability of these are going to be different. So this would be 65 over 99, whereas this would be this would be 99 minus 66 over 99. So it would be 33 over 99. So the exact path we take is going to be dependent on where our ones and zeros actually are in this path. But let's think about that. So the probability of a given path is going to be equal to the product of the probability of the result at each index in our little binary string. So looking at this, if I have my path, so we're just going to call this our path, and we say 1, 0, and then we're going to have these numbers here all the way up to, let's say this is 100. Then we want to find what the product of all of these look like. And we're going to start with some pretty basic kind of observations. The first one is that the probability of whatever happens here, so maybe I miss it, maybe I make it, the probability of that is going to be some number divided by however many shots we've done so far. So I'm just going to write some number divided by, and we've shot 2 so far, so it's going to be some number divided by 2. And then if we look at the third one, we're trying to look at things that are independent of the results of everything before, because the probability will inherently be dependent, but the one thing that's not dependent will be the denominator. So we're going to have some number, again, that's going to depend on everything else before, but we can guarantee that the denominator will be 3. And this will be the same, so we'll have something here that'll be a number over 4, and then all the way up to here, which will then be some number, and because we've shot 99 before, we'll have some number over 99. And again, we want the probability of a path like this, which is just going to be the product of all of these probabilities. So before we even have done any real thinking, we already know that the probability of our path is going to be equal to some number, which will be the product of all of these numerators, some number divided by, and then if we take the product of all these denominators, well, this actually ends up being just 99 factorial, right? Because it's 99 times 98 all the way down to 2, and we can just kind of add that 1 in because we're multiplying by 1. And now the real question is, how do we figure out that numerator? So when we take the product of all of these, I want to focus on just one thing first. Let's think about where we actually make a shot. So if we know we make 66 shots, right? Then up to a certain point, if we just look at the second one we make, because we already know we made our first one on the first time. So let's look at our second make. This will be at some index, we'll call it I, which then would say, if we know it's our second make and we're at index I, then the probability is going to be equal to what? How many makes we've done so far divided by the total number of shots we've put up. So this is going to be 1 because we've only made 1 so far, and this will be I minus 1. And then if we think about the same thing for the third, and we say the index is j, then the probability is going to be equal to 2 over j minus 1. And this will keep going until we get to our 66th make, and we'll say this is k. And then our probability will be 65, because we made 65 up to that point, over k minus 1. And now, one of the things that's important to recognize here is we have all these variables, these different indices in our denominator, but we know exactly what our numerator will be because it's only dependent on the makes so far. And the good part is we already know what the denominator should be. So if we don't worry about that and look just at the numerator, we can calculate that exactly. So if we look at all of these numerators and multiply them together, so we get the product of all of our makes kind of thing, then we will get 65 factorial, because again it's 65 times all the way up down to 1 over some number. And then we can do the same exact thing for our misses. But it's really important to note that this is a great point to be at because we have something that has this numerator that's an actual number. And then we have a denominator that, while it's not a number, we know exactly what we want this denominator, or not what we want it to be, we know exactly what the denominator will end up being. So we can repeat this same exact logic for our misses, where if we have given 66 makes, this implies 34 misses, just 100 minus that. So one of them, again, is fixed because of where we started. So then we'll just look at our second miss. And it's going to be the same exact thing. So if we say it's index I, then the probability of it is going to be 1, because we've only missed 1 so far, divided by I minus 1. And the reason I'm saying 1 and not the proportion of successes, this might be pedantic, but you can think of your probability of success being 1 minus your probability of failure, which then, instead of taking the proportion of successes, is just going to be your proportion of failure so far, your proportion of misses. And then it's going to be the exact same logic all the way up to our 34th miss, which is going to be, and then if we say this is k again, this will be 33 over k minus 1. And then the product of all of our misses is going to be 33 factorial over some number. And boom, now we've got the probability of all of our makes and the probability of all of our misses. So if we just take these two numbers and multiply them, then we also get the probability of our path, because we take the probability at each given step and multiply it together. And all we did was kind of partition it into each individual make and each individual miss. So if we take the product of those two, we should get back what we started with, which is this probability of path. So the probability of a path is going to be equal to the product of all of our makes times the product of all of our misses. And this is going to be equal to 65 factorial over some number times 33 factorial over some number. But this is great, because then we could just combine this. We have our 65 factorial, 33 factorial over some number. And we also know, remember, that we have this already equal to some number over 99 factorial. And because these are the exact same quantities, we can say that this is also equal to some number over 99 factorial. But we don't need these numbers anymore then. We don't need to use these, because we know exactly what those are. Those are 99 factorial and 65 factorial times 33 factorial. So we can then conclude that the probability of a given path, regardless of where we put the makes and misses, we didn't actually specify, we just said at some index, is going to be 65 factorial over times 33 factorial, all over 99 factorial. So if we want, so now we've got something very good. We've got the probability of a given path. So now we want to look at the probability that we have 66 ones, or let's say this, 66 ones and 34 zeros. This will just be the sum over all paths of the probability of we have this 66 ones and 34 zeros given a specific path times the probability of that path, right? So we know if we have this specific path, then this will just be equal to 1, because that path is guaranteed to have 66 ones and 34 zeros. So this sum is going to be the sum, the sum over all paths of the probability of that path, which again is going to be equal to 65 factorial, 33 factorial over 99 factorial. And now it's just how many ways, because this is just a constant, we have no dependency on what the actual path is, we can just multiply this by however many paths there are. And how many paths are there? Well, we actually said that earlier. We said that there were 98 choose 65 ways to make a path that has 66 ones and 34 zeros, given your first one is a 1 and 0. But we know what that constant is, so we can just take this 65 factorial times 33 factorial divided by 99 factorial and multiply it by however many there are, which we said was 98 choose 65. Which then simplifies if we do some algebra here and just expand this binomial coefficient, we get 98 factorial over 65 factorial, and then this ends up being 33 factorial, which is 98 minus 65. And wow, look at this. Now we can cancel, and we are left with 98 factorial over 99 factorial, which ends up just being 1 over 99. Our final answer being 1 over 99. That's amazing. So we said the probability, I'm just going to wrap this up right here, the probability of having 66 makes in 100 shots is going to be equal to 1 over 99. But we can actually go one step further and think of this in the general case. What if we have K makes in N shots? If we look back at all the logic that we did previously, what was this? What was this probability of a path that we actually did here? Well, we took all the different probabilities that we were going to be multiplying together and just took their denominator. So if we think of this, instead of being 100, then this final one isn't going to depend, it's not going to be some constant number, but we know it's some number over however many we shot before. And if we know we do n shots, then we know this is just going to be n minus 1. So the same thing here is going to, I'm actually just going to use red for these. This is just going to become some number over n minus 1 factorial. And then the same thing here. We know we make k shots. And then we go all the way up to, I can't use k here, but that's fine. We go all the way up to our kth make. And then this is going to turn into k minus 1 factorial over some number. Because again, we look at how many makes have we made before that last one. So that would be k minus 1. And then the same exact thing goes for here. This will end up being n minus k. So we're going to go all the way to our n minus kth myths, and then look at all the ones before that. So it's going to be n minus k minus 1 factorial over some number. And then we get our probability of a path being this k minus 1 factorial times n minus k minus 1 factorial all over n minus 1 factorial. And then the final thing that I skipped over by accident is how many ways are there to do this, where we have n minus 1 once, or sorry, not n minus 1. We have k minus 1 once in n minus 2 spaces. Well, again, this will just be n minus 2 choose k minus 1. And then finally, wrapping this all up, if we do the same exact logic, then we're going to deviate here, and we're going to end up getting, this is equal to our binomial coefficient of n minus 2 over k minus 1, or choose k minus 1, times k minus 1 factorial, n minus k minus 1 factorial, all over n minus 1 factorial. We expand this. I am speeding this up so you don't have to watch me do algebra that we've already done in real time. But the idea is we're expanding the binomial coefficient. We're going to cancel like terms exactly as we did before, except now we have variables, and get our final result of 1 over n minus 1. So this is the same probability. If we just plug in 100 here, we get 1 over 100 minus 1, 1 over 99. That checks. Love it. That means we did our work right. But what I think is actually really interesting about this is that although the probability at each step depends on the number of makes you've made so far, you are equally probable to have any result. I'm equally probable to score all 100, or sorry, I guess 99, because you can only make it 98 more, and I'm the same probability to score 33, to score 50, to score just 1. Those are all equally probable likely outcomes, even though in your initial probability, it's dependent on how many you've made so far. I think that's super interesting. I think this is such a cool question because your probability only depends on n and not on k. But yeah, I hope you enjoyed. I hope this was as fun a problem for you as it was for me, and maybe I will see you again. Bye.